name is Jared Luttery, and welcome to the AI Academy. Our next speaker is Dr. David Sinton. Dr. Sinton is an engineer by training at the University of Toronto, and for those of us familiar with AI, the University of Toronto has been deep in AI. And in fact, some of the earlier studies in AI and fertility date back to the late 70s, early 80s from the University of Toronto. Dr. Sinton's continuing this tradition and looking at AI applications to sperm assessment. David, I look forward to your comments. Thanks so much for participating.
Happy to be here and speak to one of my favorite topics, which is male fertility and great tools for male fertility, and specifically machine learning. And I come to this area not as a computer scientist, not as a software engineer, I'm a mechanical engineer, and I think that we came to appreciate what machine learning could offer in the sperm selection challenge. And I'm going to walk through that, what brought us to machine learning and what I think makes a compelling case for clinicians. And as I say, I'm not going to teach you to be coders here because that's not my perspective. I use it as a tool, and I think it's exciting as a tool. And one that we're going to walk through today, what it can offer, where we're at, and what are the challenges and concerns one might have around using machine learning for selecting sperm. Great. So we're going to walk through, what's the challenge? Just pick one, right? What's the challenge of sperm selection? What are we solving for? What can be improved if we do a better job of sperm selection? We're going to talk about pre-selection methods that led us, when I say us, I mean on our journey to seek machine learning and that path. And that really came through working on clinical methods, working on methods for sperm sample processing. And then machine learning guided sperm selection. I'm going to walk you through that, and then reflections on the opportunities and challenges. Great. So I think lots of folks in the audience will appreciate that male factor infertility is increasing globally. It's responsible for roughly half of couple-based infertility cases. And it hasn't had a great recent history, right? Male fertility is in decline. We don't have great data, sort of equivalent amounts of data around the world, but where we do have good data, we've got reason to be concerned. That there are challenges. And in general, many in this audience will also appreciate that human sperm samples are very heterogeneous. Sometimes in my world, in mechanical engineering, labs that are working on sperm tech work with bull sperm because it's just easier, and it's cheaper, and there's less biosafety requirements for it. The problem is it's so good, right? It's way too good to be representative. So all the stuff I show you today is with human sperm samples. But my broader point is that human sperm is very variable, right? It makes the selection challenge a real one. Our fertility journey, for me, it started with personal experience. So as I mentioned, I'm a mechanical engineer, I'm a professor, and part of the gift of being a professor is that one can pursue research areas that one becomes interested in. And I became interested in male fertility because my wife and I experienced infertility for a few years, and it was challenging. And as an engineer, I was interested to look at what the methods are that for treating fertility, and how, including how gametes are handled and selected. And so that was the start of my journey. And my background was in microfluidics, small scale fluids stuff. So that was kind of a natural starting place. So I'm going to share with you just 7 slides on that, because it's not unlike a clinical perspective. It's what brought me to machine learning as a next step. And I should advertise this paper. I'm happy to, if folks don't get Nature Reviews Urology, just email me. My email's on the first slide. I'm happy to send this to you. But a lot of what I talk about today is covered in this recent Nature Reviews Urology paper. So first thing, what is the challenge of sperm selection? What are we working for here? Reproduction is, of course, winner take all. You think about the reproductive tract, it is itself a selection mechanism, right? When natural fertilization is possible, there's all sorts of physical, physiological, chemical, biological hurdles for sperm to make it through from all the way through the tract here. And so that itself is a selection device. In clinics, when that natural process isn't working, single sperm are selected by clinician. There's of course a standard workup process, and then from a small group, I don't know how many it is, typically 10 or 100. A clinician can sort of observe in any short sitting at the microscope there, and then one is selected. And the challenge of sperm selection in cases so like in traditional droplet IVF, right? You've still got 100,000 sperm there or 50,000 sperm. The challenge of selection isn't so great. There's still that natural process that weans it from 50,000 into one when one is selected. In ICSI, of course, it's the clinician that goes all the way to selecting one, and that's a lot. That's a lot to put on the clinician, given that there's 300 million to start with. So that's the entire population of the U.S. or close to it. And, that's a lot of people. So the clinician, every time they do ICSI, is essentially drilling down to Corpus Christi, Texas, picking, some guy out of a corner store as a random example. It's a lot of cells there to select from. And human sperm are highly variable. So there's a huge difference even in a given sample. In a healthy sample, there's a huge variability. So this is the selection challenge. You got a lot to choose from. How do you sort them out? I mentioned the variability, of course, from this familiar plot. We see typical scatter. That scatter is reminding us of the variability in a human sperm sample. So we've got hundreds of millions to start, order of magnitude, and then we got to get to one. And I think of it as the sperm Olympics. How can we, how do we make it through from that set to the other? Who makes it to the Olympic team and maybe to the gold medal podium here, given this population of 100 million? And normally how that's done in Olympics is through multiple levels, right? So there's regionals, and then there's nationals, and then you maybe get to go to the Olympics and compete. So we divided this up in part because, machine learning or imaging could never get images of 100 million cells and then select them. That's never going to happen because of not maybe computing power could someday do that, but imaging could never do that. Right? You can't look at that many cells. Certainly a clinician could not look at that many cells. They'd all be dead. So we say, well, we need some process in between here, and that's a sperm workup method that we've developed here in labs and practice right now. Density gradient centrifugation and swim up are used, and then here nationals, right? This is where we think there's a role for machine learning. You've got some reasonable number to image. You could image those and use machine learning to select the one. So that's the role we see for machine learning. Now, first on the regionals, and then we'll get to the nationals. So in the regionals, there's been lots of great work done in this area. I'll take you through all of this. There's been some great devices. I think one that's seeing commercial uptake is the Zymot device, which looks a bit like this. This is an early kind of version of that, but there's sort of a bit of a channel run here, and then a filter that sorts out some sperm for selection. I think this was originally conceived for droplet style IVF and IUI. This is our stuff on the right. We've got these small scale channels. We put sperm around the outside and they swim in, and then we've got some different paths that one can take. They can select sperm that turn left or turn right or do different things, different labyrinths essentially that you can put sperm through to select them. Here we're sort of mimicking. Remember we looked at that that female reproductive tract, and like all of the challenges along that track that the sperms face on the way to the egg. We're kind of reproducing that here. And here's an image of, you can see the sperm on the outside of the ring here. We're zoomed right in. So some of the little guys can make it inside. We've dyed them here so we can see them. And then they swim along. Interestingly, they swim along the edges of the channel. It's typical. You know, they're trying to win that race, right? So they're going in the regionals, and if they get to the center on time, then they'll get a chance to compete in the or they're in the nationals, I suppose. Great. So this existing Zymot device is a nice commercial offering available now. You know, when we think about our methods compared to this, we look at the number of sperm selected, and the volumes are very low. It can still work really well, but the volume of sample that comes out is quite low, and the number of sperm that come out are quite low. We've had other devices like this one here. We can get up a little bit, but both of these present a trade-off. You get high quality sperm out generally, but you don't get a significant quantity. And clinicians tend to demand, even though there's only one sperm maybe going into the ICSI, clinicians want to know that there's going to be a lot of sperm available for them to test. They don't want to, it feels risky to put their patient's sample, especially if it's not a great sample, to put it in a device that's not going to return a large quantity of good quality sperm. So that's the challenge. So this, again, inspiration from the female reproductive tract, and all of these channels and all of these crevices really give it multiple paths for sperm to swim up and work their way and show their strength. This avoids a quality trade-off, right? Because there's a lot of roots here to the egg. So we tried to mimic this. So we've got a little device here, and we put these guys, we put the sperm sample in the bottom of the tube, just like you would for a swim up, and we drop the device in the top, and it has some buffer on top, and then the successful sperm swim up through these channels all the way through. So this is a lot like, if you think back to that reproductive tract, it's really mimicking that. You know, and as a result, you get selection of sperm up into the top. And since there's a lot of channels, you got a lot of high quality sperm. And that's what this is showing. We get a couple 100,000 sperm of good quality. And here's the quality quantity trade-off here. You think about it, so these are different samples. This is lower motility. I know, and you're thinking, right, lower motility, probably lower quality sperm sample. That's right. And here we've used the DNA fragmentation index, right? So here for the raw sample, really high, lots of DNA fragmentation, not a great sample here. And then of course up in here, pretty good samples, right? So the DNA fragmentation is less in this case. Up in here, this good sample. And then how did, you know, density gradient and swim up do? That's the red line here. So some improvement from the raw, no question. But the 3D device that we've developed is better, right? So down here, the really exciting thing is these ones. This is not a great sample, right? These are the not great samples. And we were able to pull out pretty high quality sperm. So look at this. So this is a good sample. This is a poor sample. Coming out of the 3D device is almost the same quality of sperm. It's a pretty flat line. So that's really the quality quantity trade-off broken. We think. And in the same case here, how many did we get? This is quality on this left-hand side. This is quantity on this right-hand side, right? We're able to get, you know, tens of thousands of sperm, even from the worst samples. So that's, that we think has promise. And we were really fortunate to work with the Hannam Fertility Center in Toronto in developing this. Great. So we've got a solution here for what we think of as the regionals. And then in your clinics, you may, you know, if you don't like this kind of approach, you may say, well, my density gradient does a good enough job for this. That's fine. You get to some large number of sperm. And then the question is, what happens from here? And this is where we get into the machine learning piece. So machine learning, the way to think about, you know, there's a lot of buzz around around AI, machine learning, deep learning. For today's purposes, and frankly, for my purposes, I think of them as all the same. Deep learning is a form of machine learning that use recurrent neural networks, and you can just think of it as a bit more advanced, modern machine learning. Excuse me. So don't get hung up on those distinctions. Certainly, computer scientists that are right in the field are very specific about these. You and I don't need to be. Machine learning, AI, deep learning, it's the same. What are these things? They're prediction machines. Okay, they're prediction machines. That's what they're good at. So they learn through past experience, through studying markets, or through, in our case, looking at images of sperm and getting DNA data from sperm cells. They learn what is a good sperm cell. Or they learn, in this case, in AlphaGo, they learn, some of you will be familiar with this game Go, and it's a very interesting and cool board game. And AlphaGo Zero was an algorithm that mastered the strategy of Go. And one little twist on the AlphaGo narrative is that the machine trained itself. So the stuff I'm going to show you today, it's called structured learning, machine learning methods. In other words, we taught it, or we used DNA integrity data to train the algorithm to recognize high quality sperm. AlphaGo didn't need that. AlphaGo just knew the rules of the game and played itself, and it mastered the game in a short period of time. And then you can see the picture here, beat an AlphaGo master. Or a Go master, probably. So, but we're talking about a different thing than playing a board game. We're going to talk about structured learning. We need to train our algorithm as to what makes a great sperm. So this is the progression of over, this really has a long history of machine learning back to the 50s and 70s. What we currently know now as deep learning it uses multiple layers, recurrent neural networks. This is more modern, and there's a proud history of developing this at the University of Toronto here, and Google via Geoff Hinton's work. So this is really the modern deep learning we're going to be talking about today. There's all sorts of different forms of this that have been applied in healthcare to date, and you can imagine it depends on the application. In some cases, you've got cell traits as input, and you get some cells coming down a device, and you want to make a decision. Don't forget, these are prediction machines. So this one's going to predict the cell class of this thing. It's going to say, that's a red blood cell. That's what this algorithm is going to do, right? So the input's a trait, the output's a cell class. You could think about some sort of engineering thing where you've got some voltages, and you're going to predict the pressure inside this device. Maybe what's coming in is a sequence of events. You get some DNA going through a nanopore. Then you want to predict the DNA sequence. That's what's the output. It's a prediction machine in the middle. In our case, we're going to be talking about sperm today, and that's a situation where you've got an image of sperm. Clinicians, they work with sperm under a microscope. They see them. They make a judgment. We're going to have the AI do the same thing, and it's not going to produce an image. It's going to produce an output and a decision, a ranking of that sperm in terms of sperm quality. So in AI speak, that's what you call image to unstructured. We're going to get images are our input data, and we're going to have a judgment, a score for that sperm. Same thing a clinician would do looking at sperm under the scope. Some misconceptions about machine learning, the amount of data. So the statement would be deep learning image analysis requires big data, millions of images. It's not applicable to these kind of applications or sperm selection applications. You only got 1,000 images. Okay, that's not true anymore, largely because there's pre-trained networks. And maybe you've heard about networks that have been trained on the internet. They've been trained to recognize cat images, right? That's a cat, that's a bus. I know it seems ridiculous, but when an algorithm has been taught to look at an image and assess the image, even if it's been trained on cats and buses, that's a useful algorithm that then one can apply to looking at sperm. So in other words, you've taught the algorithm to see. Does that make sense? So you don't need to teach your algorithm to see only sperm cells, right? It can learn to see through other training mechanisms. You could just buy an algorithm that's been trained or download one. So that's a misconception. The other one is I guess on the tech side, you got to compete with Google. You got to hire the best AI person to do your thing. No, this is becoming an established technology, and I'll make the case later that it's really not the hard part, right? The algorithm is not the hard part. That's becoming established, and you really can have an engineer not in this area. I just locked an engineer in a room for 6 months with YouTube videos and some good research papers, and they came out able to apply AI to sperm selection. There was food in the room, and there was there was light and stuff. It wasn't so bad. Okay, so I won't take you through all the details here, but what are the sort of things we're looking for? We're looking for the same stuff clinicians do: normal shape versus tapered versus other abnormalities, right? How can we predict those? So there's been some early studies on this, and so the sperm the image is the input to the algorithm, and then there's all this inside the algorithm. And machine learning approaches have really been able to get up to a true positive rate, high positive rate of being able to predict similarly to clinicians. But we want to go one step further than that. We want to be able to train based on data on specific sperm cells. Here's an example of an algorithm looking at sperm cells and judging them, so you can sort of see how they're being judged. These profiles show where the algorithm is focusing, where it's making its decision. Here it's narrowing. It's like, look, something's not right here. Something's not right here. This is a piriform cell, right? So it's tapered, and the algorithm's zeroing in on that. It's like, I don't like that. That's not right. Same thing a human might do. And then here, amorphous, here it's looking at the whole profile and assessing it. So it's interesting to see. We can't always see what's exactly happening at each layer in the algorithm, but we can see where it's focusing, and that gives us some confidence. Yeah, this guy's figuring out that this is a piriform cell. Okay. Now, we didn't want to rely on humans saying that's a piriform cell, teach the algorithm that that's a piriform cell, and go from there. What we wanted objective data of sperm quality. So there we turn to DNA integrity. And those in the male fertility world will know that DNA integrity is not the only measure. It sounds great. It's quantifiable. We can measure it. Engineers love it. Many clinicians love it for that reason, but it's not the only measure, right? There's other factors, including morphology, including motility. Nonetheless, this is what we had to work with. So in our first training work, we worked on getting DFI for a whole lot of cells and getting images for those cells. So this is exactly what the clinician would see, right? And then we found out, okay, perfect, that same cell, what was its DNA integrity? So we were able to, this was a ton of work, but we were able to build a training set where we knew the right answer and we could train our algorithm. That's the key thing. We knew the right answer. In this case, it wasn't a human opinion of this cell is good, this cell's bad. It was the DNA integrity data. So here was 1,000 sperm from 6 different donors. And we measured each one. And then we trained the algorithm on it. So this is a sample of some of the images. And you can see lots of variability in this sample, right? Lots of cells here. Experts are saying, oh, I don't like that one. I don't like that one. I don't like that one. Let's play a game. Some of you, like me, are old enough to remember Wheel of Fortune and Vanna White. So let's reveal some sperm candidates here. And I don't know what the phrase is. Okay, so have a look at those and try to think, okay, which ones are for sure not good in our judgment? We're going to compete with the algorithm here. And that's a not good one. Maybe you pick that one. That's a not good one. If you pick that one, that's right. And that one too. Yeah, not high quality. And in terms of some favorable ones, right? These orange ones, these were determined by the algorithm to be decent. And it's interesting that and by measuring their DNA integrity, it's interesting that not all of the good ones here that I would have picked are on the good list. And if we do a more systematic comparison, we're like, okay, well, what do we machine predict versus measure? And here, of course, if the machine was perfect, if the algorithm was perfect, the predicted ones would measure up right along this line. Every time there was a 0.15 DFI cell, it predicted exactly right. And here's a case of a 0.15 DFI cell, fairly low quality. It's one of the higher DFIs in the whole sample. And here's interesting, right? It's right on the line. So that means that the predicted 1.15 is exactly what we measured. So the algorithm really got this one right. And I would say did better than I would do. I would have said this cell is not that bad. It's kind of maybe better than this one or better than this one. I would be wrong. The algorithm and the measurement agreed very well there. How about down here? These are good cells, right? These have low DFI. How did the algorithm do? Pretty well. You can see these are some of the ones selected here that were predicted was a little better than what was measured, but all considered good cells. And here measured was a little higher than that predicted. And as I mentioned, the surprising things are some of the ones here that were predicted to be high quality, measured to be high quality, but I wouldn't have necessarily picked. Sample enrichment. So when we think about what could this do, if we just took these green guys, instead of gave these to the clinician as AI down selected ones, what would we get? And you think about a histogram of cells that this clinician would get in the full sample. And then we said, okay, AI, pick the best one, pick the very best one. In this case, in this run, the AI would have picked this cell. So it would have been, this one, which is pretty good, right? That's a heck of a lot better than all of these low DFI. This particular algorithm didn't nail it, didn't get the very, very best one. But this, you can sort of this distribution in realms of biology, this is quite powerful. This is looking like the selection process is quite good. So we run a bunch of different donor samples, as I mentioned, and you look at how did we do picking the best sperm or the best 20 or 30 sperm or 10%, 20% sperm. You can see the different profiles here. In these two cases, right, this was the gold medal match here. The algorithm actually picked the best sperm in terms of DFI, very impressive. Here it did still okay. It always does reasonably well with the overall sample. Here donor 2, not as good. But I think we're getting some sense for the efficacy that the down selected sperm, the ones that the AI, the machine learning says, yep, these look good, tend to be higher quality. When we asked our embryologist friends to do the same thing, and they're good sports, they say, okay, we'll do this Paul Bunyan men against machine test, right? They selected a subset that they thought were normal versus the abnormal. And compared to measured DFI, they picked relatively few terrible ones. That's good. But the sample wasn't that enriched. It wasn't that much better than sort of a random selection. Versus in general, we were able to down select further and better with the AI. And I think there's a role for these two great experts, the AI embryologist and the embryologist, to work together in future. Few comments on this. Will machine learning replace the clinician? And I think the answer is pretty definitive, and it's no. It's likely to be an assistive role, but I think likely an important assistive role. And when we see AI, machine learning being applied in other sectors, there's lots of precedent for not replacing the expert, but rather helping them do better work, help them in the work faster, and as I mentioned, an assistive role. But I see no future for AI replacing expertise in the lab. What's the nature of the nascent business or industry? And there are good machine learning things available now for embryo assessment and to guide clinicians in that area. I'm not sure if there's one for sperm yet. I say that because I'm hopeful there is a commercial offering. Hopefully there will be soon, if not. but it will be winner take all. So like lots of things in the algorithm space, it will be winner take all. In other words, the best trained algorithm will gain the trust of clinicians, and clinicians will trust it because other clinicians trust it, and it will become the standard. What are the limitations and concerns re machine learning based selection? I think there's lots. Our algorithm was trained on 1,000 sperms, 6 donors. That's a good, for a good first study, for a good assessment of could this thing work? I think that was very useful. I think it did indicate that there's real promise for this. Is that enough? Is that enough to head into the clinic and start selecting? No, it's not. So, what all of the questions around training AI, which you may have heard in medical sectors, apply here. Is it representative, right? Are all of your donors are probably all male, but are they all white males, right? Are they all white males from one area, from one region, right? As we saw in our original map, male fertility does have global variation, and the algorithms that gain the confidence of the community will need to prove that they're representative for the population that they're assessing. So there's representation issues always front of mind. What about how well is it trained? I mean, 1,000 cells, it's a lot when I have to ask a grad student to do it, but it's really not a lot. We need far more numbers of donors, and we need a far bigger data set. The good news is, and this comes back to the winner take all point, once a technology is introduced in labs, you can bet that there'll be a data clause on that technology. So the data will go back to the company that's developing the algorithm to improve it, right? Just like you click that box when you're doing Google, signing up for Google Docs or something, that you'll allow them to improve their services based on your data. Same thing here, right? So the more it gets used, again, winner take all, the more it gets used, the better the algorithm will become. More concerns. I use DNA integrity to train it, and that's because it was an objective measure we could get in the lab. It wasn't a human opinion, and that has value, but it's not the only measure, right? So you can imagine a truly capable machine learning system for sperm selection will take into account the things that all the clinicians do: motility, and other factors. Who will win the business and confidence of clinicians? I think I answered that in the last few slides here, and this one in particular. It really will be the algorithm and the approach that has the representative data sets, huge database, and is applicable around the world. So in summary, what are we solving for here? Sperm selection is a challenge. It's a fundamental challenge. You've got the population of the US, and you've got 10 minutes to figure out whether you're going to take somebody in New Jersey or somebody in Sacramento. It's a massive selection challenge when you think about it. And it wouldn't be a big deal if they were all the same. They're not all the same. There's huge variability in human sperm in terms of their quality and whether they'll produce they'll result in successful pregnancies. Machine learning can help with this. Well, there's a range of technologies that can help. Machine learning can't help with 300 million. It's too much. But there's great sperm tech, and I advertise our approaches there, and there's other ones in selecting down to 10,000. So 300 million to 10,000 sperm. But from 10,000 on, you're really getting into the clinician selected application. And here we think machine learning can help clinicians. It can help them see more sperm, assess them, and then maybe provide a pool. Say, hey, this is 100 great sperm, or this is 50 great sperm that we assess to be very high quality. You, clinician, go ahead and make the final decision. Maybe that's the ultimate use case. DNA quality, quantity, and representativeness, if you can say it, will determine the net utility. That's where the battle will be fought here, and hopefully these tools will be available to folks commercially very soon. Great. And with that, I thank you. Hopefully that was useful. And yeah, it's been a pleasure. And as I mentioned, if there's questions or if you want some of the literature that I pointed to here and don't have easy access to it, don't hesitate to use my email on the first slide.
That was great. I know there's some embryologists. I don't want to risk observer fatigue since this was a little bit over. That was an excellent presentation. I'd encourage some questions. I know there's some embryologists here or comments. I'd love to hear, Eva, what you're thinking or what the other embryologists on the call might have to comment. We've been at this using a computer to look at sperm for about 40 years, dating back to Darkfield, trying to track the path of the sperm to get the best sperm. But I think this is right on the edge. Not quite ready for prime time, but I think we're getting to the point where this is can be useful. A couple things I'll comment on, and then we can end if there are no other comments. In the history of IVF, looking at the animal industry has always been kind of a bellwether as to what's going on out there. Certainly not one-for-one transferable, but there's a tremendous amount of activity in the animal industry looking at computer selection of sperm. Probably far more publications than there are among humans, just to give you some sense of this can happen. And the second thing I'll comment on is one of the points David made is this concept of reducing uncertainty. We're always looking to reduce the uncertainty. And statistically, you never get to certainty, which is 1.0. You might get to 0.9. Anything that will reduce the uncertainty, for example, in the lab of sperm selection, is an advantage. Our patients always ask, how do you get the right sperm? And the answer is, well, we kind of get close, but I think we can do better. So I think with that, we can end. This was an excellent lecture. I especially like David's use of the Olympics of regionals, nationals, and finals. That's a great term. And this clever little slide with the quiz show. So we can end. Thanks so much for participating. I'm really encouraged to see the number of people who have shown up. Our next one is with Alice Domar, talking about applications of a smartphone to helping reduce the anxiety and emotional turmoil that fertility evaluations can cause. So with that, we'll sign off. Thanks to all.
I think, Gerald, we have one question.
Yes.
In the chat. I will read it for your convenience. Yeah. Dear David, thank you for the presentation. Kindly ask you to comment the following. Do you think that the machine AI would be able, so I think that's still some part, to process the whole sperm sample, probably?
Yeah, so great question. I think what David's not participating in the call. I'll speak for him at the risk of making a mistake. But I do think that's where we're headed. Initially, speed, velocity, and direction were the original CASA, or computerized sperm assessment tools, relatively rudimentary 40 years ago. But that is exactly where we're headed. I think a combination of looking at structure, movement, motility is what's going to identify the best sperm and reduce this uncertainty in picking out the best player. So great question. Any others? If not, thanks for your participation. We'll see you in 3 weeks to listen to Alice talk about her tools.